Hello everyone and welcome to the Uppaal tutorial. To begin, you have to download it, so you should go to this website, uppaal.org, and yeah, it's free for non-commercial applications, so you can go to downloads, select whatever system you're running from, and yeah, just follow the instructions there. You might need to install some other stuff as well, like some Java things, but you should be able to do that easily. And let me tell you before we leave this site that there's plenty of interesting material over here. You can come to and reference it. It's very useful and very interesting, so keep it in mind. There's a short introduction, there are examples that you can look up, there's plenty of stuff to do. So I'm going to assume that you have somehow installed this, and we're gonna go on with the tutorial. So I have it installed somewhere, and I'm gonna run it. This is how I run it. Probably from some other machine you can run it differently, but that doesn't not important. So now you have an empty canvas in front of you. This is a new project, and this is what we call a state. Now in Uppaal, what you model is timed automata basically that interact with each other. And right here to the side you see a template, and that's basically what you're looking at right now. This empty, this just alone state is this template that I have not added anything to. And each template that you make is a different timed automaton. Automata are things that are changed from state to state. So if you add more than one state and arrows among them, then you have some rules that are going to be followed, and the automatons are going to switch states and communicate. Now, how do they communicate? They use what is called as a channel. A channel is basically a variable that is global, so you're going to declare the channels as global declarations, like so. So I'm going to add a channel, and for the purpose of this example, I'm going to name the channel coffee. Now there's a channel coffee, and the various templates that I will make are able to use it. And how are they going to use it? They're going to be producing inputs and outputs on this channel. Now, to produce an output, for instance, in this channel, I'm going to add an arrow, so this state can transition to itself by shouting coffee. And the shouting part, so the output, is made by adding an exclamation mark to the channel that you're using. So now I have a little process here, a little timed automaton, that it can transition to itself, to the first state, by shouting coffee. So I'm going to call this template a computer scientist that requests coffee in order to proceed. And when you have an output action, in order for your system to work, there should be another process, another timed automaton that is inputting this action in order, and this is what we call a synchronization. Now note, when I added this action, I added it at the sync field of this edge, because this exact action is going to be used in order for two processes to sync together. And I'm not going to add anything else yet. I'm going to go ahead and make another, cancel. I'm going to go ahead and make another template that's going to be the template that accepts this action, that receives it. So I'm going to insert a template, and I'm going to call it a coffee machine. And now it just by default creates just one state. So that coffee machine is responsible for receiving orders of coffee from computer scientists and producing the coffee. So I'm going to add another state. This part of the creation of a model is up to you. You can be as creative as you want, as long as you're loyal to what you're actually modeling. So I made another state, and I'm going to say that in order for the coffee machine to take this transition, it needs to be, something needs to be clinked. So for instance here, the machine was given the input coffee, somebody is asking for coffee. And yeah, I could add an arrow as well that takes us to the initial state, back to waiting for something to happen. Now this is a very simple and I would say trivial system, but let's compile it. And to compile it, what I've been doing so far is I go to the simulator. It tells me there is a model in the editor that is not loaded. I say yes, and it tells me that it has initialization errors, and that's always the case. So you go back and now you can see your errors down there, and it's going to tell us that we don't have a template. That's very good. It just means that I have not declared what the whole system is made of. I have just declared some mini automata, some mini processes, that I have not told the whole system, the simulator, what to run. So now I'm going to go to the system declaration and say, oh, okay, it has some preset values here. So it's defining a process as a template with no input, because we have not inputted yet anything there. And I have renamed it, so there is no such thing anymore. I'm going to rename this as computer science. And I could do that as well with a coffee machine, but instead I'm going to prefer doing something easier and just go ahead and do this. So now I've told my system that this is what you should simulate when you run the simulator. It tells me that something new has happened. Now we have syntax errors. Maybe I should not have added the parentheses there. Let me delete them and see. Yes, okay, so now it created a system that's made of these two processes. Now this is extremely simple, and also it's, but let's, so now that you're at the simulator, you can try to run this thing, and you can try a random simulation. And as you see, the coffee machine starts producing coffee. Obviously, as you see, the edge here is getting red, so that means that the coffee, the computer scientist is requesting coffee. Now I'm going to halt, this is not very interesting, and start adding interesting stuff. So I'm going to go to the computer scientist and say, okay, you cannot ask for this coffee all the time. You need a cooldown period. And how do we implement a cooldown period? I'm going to add a guard that says that you have a cooldown, some variables called cooldown, and I'm going to request that this variable is bigger than 2 time units. And once you've not cooldown, yeah, cooldown. So in order for you to request coffee, you need to have this value larger than 2. And I'm gonna say that once you've had coffee, this cooldown becomes 0 because you've just had coffee, allegedly at least. So once you request coffee, you're not allowed to request coffee until 2 time units have passed. So now I added these, I can move them around so that it looks nicer. Okay. So now you have a computer scientist that as long as he has waited for 2 time units, he can request coffee, and then he has to wait 2 more. And I have not declared this variable, and so I have to declare it. Now what did I say this is? It's a time thing. So these are called time variables, and basically to declare them you need to declare them as clocks. Now this variable is local only to the computer scientist, so I'm going to declare it in the local declarations. And how do you declare it? You just say clock cooldown. Now clocks are a very particular type of variable that once they've been declared and accepted and compiled, then when you run a simulation they immediately start increasing in their own tempo, which is completely local, and there is no interaction with it with the other outside world. It's just something internal happening in this little mini automaton here. And the only way to access them is by updating their values on these arrows. So I'm going to go to the simulator again, we have some updates, it compiled immediately. Okay, so now the computer scientist needs to wait a little bit while asking for coffee. And what else could we do? Let's go to the coffee machine, and I'm gonna say that, okay, the coffee machine also cannot produce coffee all the time. It also needs to cool down somehow. So let's say that once the coffee machine is asked for coffee, it will go to the state where, okay, it's gonna make the coffee, but in order to go back, it needs also to rest a little bit. So I'm going to add the rest clock, and say that let's say that in order for the machine to rest well enough, it needs one time unit. So in order for it to be ready to accept orders again, the one time unit needs to pass. And of course, as it takes this edge and goes to the situation where it can indeed accept orders, then I'm going to reset the rest clock. This is just for this particular example. It doesn't have to be like that, but yeah, depends on what you're modeling each time. This is just a general overview. Okay, so we have two more things, and I have not declared this clock, so if I try to compile it, it will tell me that I cannot. I'm going to go and declare it. This is a clock variable, and it's a clock, well, what did I call it? The rest clock. And I make a lot of typos. That's true. Okay, I've declared the rest clock. Good. So let's see if it will work. Try something new. Okay, it is working for now. Let's try to do a random simulation. Okay, and things are starting to happen. It seems alright. Now, what's the problem? Not necessarily a problem. First of all, you can go and look at the local variables of your processes by looking at these things over here. And in this particular scenario, they're not very interesting, but just have it in mind for the future. You can look for a specific execution of your system. You can go and see what values your variables have taken throughout this execution. Now, what did I just say? I said that, this looks alright. I'm pressing a random simulation and it seems as if it's working. The process this process is requesting coffee, and the coffee machine keeps producing coffee. But this is just one execution. And what the problem is that you can't really know what's going to happen to every execution, and that's where the verifier comes in. The verifier is this tool here where you're going to ask some queries, and it's just going to tell you if these queries hold for the thing that's loaded in the simulator at the moment. And how you write down queries is the following. So you have your templates, you have all of these things. So you go to your verifier and you have two basic things. One is whether you want what your criterion for success is to hold for every execution or for just one execution. An example of this is that, for instance, you want for every possible simulation that it never deadlocks as a system, so it won't get stuck. So you probably want no execution to deadlock. And in order for you to write down that all executions should do something, you write down an A. Now you get, okay, I don't want all of my execution to deadlock, all of my executions to deadlock. But what if you wanted to refer to some specific point in time, or rather something to establish a specific point in time of the execution? Now, there's two ways to refer to the points of your execution. To write a query, you can either refer to any point of the execution, in which case you write down this by using these two symbols, and that means that in all of my executions from the A, all, in some state something happens. That's the query you're going to ask with this syntax. Or you can write down in all of my executions in all of their states. So in all of my executions and everything that happens throughout them, and then whatever you write down you want it to happen. So in my case, I want to check if there is at least one execution. So I don't want for all of the executions. I just want to check if one of them if one of the executions deadlocks. So I'm going to write down E for exists, and then an execution where at some point in it deadlocks. So deadlock is a reserved reward, and you can write down this query as so. And I'm going to go and press check, and it tells me that the property is not satisfied. What does that mean? That there is no execution where at some point the system deadlocks, and that's great. That's what we wanted. I've been looking for. So what I wanted to say is that if I wrote down a query like for all of my executions, all of their states are deadlocked, and I expected that this will give me some interesting information, I would be wrong, and that would be my problem. So the way you write the queries is up to you. Or if I had written down all that exists. And what would happen, let's say that this runs, and it tells me that the property is not satisfied, that not all of my executions deadlock at some point. Well, the fact that this is not satisfied is not very interesting, because it just means that for all of the executions they do not deadlock. It doesn't mean that there doesn't exist one that deadlocks, and that's what I wanted to look at. Now, as a final note, this is a very simple model, and there's a lot of things you can do with it. A very important one is, let's say that a final thing basically for this demo is that, okay, I'm going to the computer scientist, and we said, okay, for him to request coffee again, he is going to have to wait at least 2 time units. But I'm going to go ahead and say that, okay, the computer scientist cannot function a long time without coffee. So what does this mean? That while he's working, while he's in this state, every once in a while he's gonna want to follow the arrow. Since this cooldown clock is always recording and it's always increasing, I'm going to use this clock and say, while you're in this state, you can only be in this state mainly while the clock is not very big, so it has not run for too long. So this is my cooldown clock, and I'm going to say that you cannot be coding for longer than 4 time units. So if you want to be in this state where you have not followed the arrow and reset your clock for a long time, that time is only 4 time units. So I've added this invariant on the state. What does this mean now is that you cannot be in this state anymore if this invariant is not satisfied. Basically, you have to leave. If the clock is almost ready to go to 4, the time unit 4, you have to leave the state. You can no longer be in it. So you have to follow the edge and ask for coffee and reset it through this edge. Now, again, the fact that you reset it is based on the fact that you've written the model correctly. If you had not written this update correctly on this arrow, that every time you follow it you have to reset the clock, then the clock would never reset, and that would be a system that deadlocks, because you cannot go back to these states, but you would never reset as well. So I'm going to load this model again, if it's correct, and I'm going to press a random simulation, and it seems alright. Okay. Now, there's plenty of stuff to do, and while you start doing things, you can write very complex things here as well, in the local declarations and in the global declarations of the system. If you want to implement some more intricate checks for the verifier, you can define some Boolean variable that goes through your templates and finds something, like maybe that all states have been visited or something like this, of something, and then you can check if this variable level ever becomes true. So you can do quite a lot of complex things, and as a final note, you can go to here, press help, and go to the language reference, which is somewhere here, there it is, and basically if you open this, you have a full documentation of the language and the modeling tools behind Uppaal. So you can do lots of things. This is how to declare variables, this is what to do with new templates, your system definition over here, It's very interesting. There's a lot of flexibility in what you can do. And there are some reserved keywords like deadlock that I used already, true, false. You can write if statements in your methods. And for the specifications, so for what your system should be doing, this is how you define them. All and then box, or and then this diamond thingy, that this means for all paths, for all states, for one path at some state, and so on. And you have finally this semantics tab that explains a little bit of what, when you write queries, what do they mean, so what you will be looking for. And that's what I mentioned when I said that writing the correct query is up to you. You need to be understanding exactly what the operators are doing. So you should take a look at this specification language so that you can write the correct queries. And that's it from me.